Alrighty, so here we have Chapter 12 homework. Say this is Ethan Seprin. Now we got 9 problems. And yeah, let's get started. So, first problem we have is tugboat pulling a small barge through harbor. Propeller thrust minus the drag produces a net thrust. We are given that is linear with speed, so the force is equal to 81,000 minus 27,000 V. And then, let's see, knowing that the combined weight of the tug and barge, that 3,600 kilonewtons, so 3.6 million newtons. We need to determine the time required to increase the speed from 1 meter per second to our final value of 2.5 meters per second, and then the distance traveled during that time. So what we have our F equals ma, and we know that the acceleration is equal to dv over dt, so change in velocity over the change in time. And so what we can do is, so we know that F, or the force, is equal to 81,000 minus 27,000 times V, and we can set that equal to our mass, which is our weight divided by gravity, or weight over gravity. Actually write that in, equals weight over G, and that's where we get that from. And so we get, after plugging in and doing some algebra, we end up over here, and we get our acceleration is equal to 81,000 minus 27,000 V over 366,972.5. And so now that we have, again, knowing that acceleration is equal to the derivative of velocity with respect to time, we can move along and rearrange some things and create some integrals. And after doing some calculus, we can solve for 0 to t. That gives us a time interval, which is what we are looking for, from what it takes to get from 1 meter per second to 2.5 meters per second. And I solved this doing some u substitution here. I just found that as the easiest. And change the values up top to fit so you don't have to go back. And I get t equals 18.84 seconds, which I believe is the correct answer. Yes. And then for part B, we are looking for the distance traveled during this time interval. So a way to do this, or how I did it, is we know acceleration is equal to the derivative of velocity with respect to time. So we can, instead of dv over dt, we can do dv over dx times dx over dt, which you might recognize this as just velocity. So we already, or actually, I don't know if we have, looking back, we can, just v dv, looking back, this is the first problem I did, so it's the least fresh in my mind. But v, the integral of v with respect to dv, that is easy, because we do have our initial and final velocities there, so we can do it with respect to that. Or we know the intervals that we're looking for. And then with dx, we can find 0 to x. That gives us the distance traveled over that time. And so, again, doing some calculus, again, I did u substitution. U equals 3 minus v, so v equals 3 minus u up top, so we can change the bottom and top to these values right there. And we change those values as well. And then I separated them out into two different things. I'm sure that there's somebody better at calculus than me that is able to do that, but it ends up being 3 over u minus 1. So it's just easier to divide and conquer. And so, again, after some calculus, we just go through and we discover that x equals 36.14 meters. So yeah, biggest step, again, just understanding this relation, that velocity can change with respect to x, displacement, and then the velocity is just dx over dt. So that's how we were able to manipulate our differential equation. And then we already did that guy up top, just for more space. Let's see, problem number 2. We have a 5,000-pound truck being used to lift a 1,000-pound boulder that is on a 200-pound pallet A, knowing that the acceleration of the truck is 1 foot per second squared. So we know it's going that way, accelerating at 1 foot per second squared. The horizontal, we're trying to determine the horizontal force between the tires and the ground, and then secondly, the force between the boulder and the pallet. So that would mean how much the pallet is pushing up on the boulder. Obviously, from statics, we know that they push each other, but we're just worried about the force on the boulder. Yeah. And so, one thing we know here, it's important to look at, see, this goes over the pulley and there. So the length of the rope is always constant. We have that there. And so, right. So I just have this as our x part, and then we have 2 y's there. And so the velocity of them is always added up to 0 if you take the derivative of that. So constant equals 0, and the acceleration is always equal to 0 as well. And so that part doesn't matter so much. It's just to get down to that part is what we need. So we know that the acceleration in this direction is equal to 1 foot per second squared. And so sub in 1 there, which ends up being over there. 1 plus 2ay equals 0, so we get ay. It's also important to denote that I had that set up as in y is positive going down, so we get ay equals negative 0.5 meters per second squared, which just means that it's going up. So yeah, there we have that. And let's see, we have a little free body diagram of the truck here. So we know the truck's outputting a force in that direction. You know, there's a tension in that direction, and then weight and a normal force. So, let's see, make sure I'm doing this in the right order, I believe. So, we know the mass of the truck is equal to the weight of the truck divided by gravity. We're using imperial units, and so I guess I didn't know these denoted slugs at first, but we learned, and we just kind of put everything in terms of, I guess, slugs are just in imperial pounds and such here. And so, let's see, for part A, we know the mass of the truck, and so we know F equals ma. We know the mass of the truck. Right? What am I? No, sorry. We need to find the tension first. Sorry. So we know the acceleration of A and B. They move as one. They're moving in that direction. So we know that there are 2 ropes on them, as you can see here, pulling up. And so that means it is 2t. This is our free body diagram there. So we know that net forces is 2t going up, and then minus the weight of A minus the weight of B is equal to the mass of A and B combined times the acceleration. And so we're doing this to find the tension because we know all of those at the moment. And this is where we needed to do those to find the masses. And we end up getting, after a bit of algebra, we find that the tension in the rope is equal to 609.3 pounds. That allows us to determine the force over here, because then we just found the tension, and we know the acceleration and the mass already, so it's just plug and chug. The force of the truck is equal to 764.6 pounds. It's actually in that direction. Then the force between the boulder and the pallet, and so we know the force that is acting on it is equal to both, let's see, or this is just the force between A and B, which, if you look up here, the ropes are connected to the bottom, so it's all just going straight up into B. So, and we know that the acceleration of AB is 0.5 meters or feet per second squared going up. That's our kinetic diagram. So we know that the force of AB minus the weight of B is equal to the mass of B times the acceleration of AB. So again, a bit of algebra. We find that the force of AB is equal to 1,015.5 pounds. So that's the force. Again, that's the force between the boulder and pallet. For question number 3, we have a 450 gram tether ball, I guess 0.45 kilogram, is moving along a horizontal circular path at a constant speed of 4 meters per second squared, so that means there is no tangential acceleration. We need to determine the angle that the cord forms with the pole and the tension in the cord. So what we can see here, I guess I don't know if it's good. I end up combining diagrams all the time. But that's 1.8 meters long, and we know that there's a force of y, and we know that this is in tension, and then that's the force of x in tension there. And so, as I said, tangent acceleration equals 0, and we know that the normal acceleration is equal to the velocity squared over the radius. And so we know that velocity is equal to 4 meters per second. And so in the f, or in the x direction, we know the acceleration is only normal. And so, or it always is. And so we know that it's the mass times the normal force is equal to the net forces. And we only have one force in the x direction. Yeah, and I mean, we have another free body diagram there as well. Actually, that was from a trial run. So we know from our free body diagram here again, this is f of ty, f of tx. And we know that f of y is equal to the mass times the acceleration in the y direction, which is equal to 0. So we know that the y forces must cancel out, and we know that since there's only 2 of them, they must be equal to each other. So we know that ty, which is equal to t cosine theta, is equal to the weight, which is 0.45 times 9.81, and we can get a value for tension, and at least a placeholder for tension at the moment until later. And then for forces in the x direction, there's only one, tension in the x direction. And so we know that is equal to the mass times the normal acceleration. Again, no tangential acceleration. So we know that the radius also must be the length of the rope times sine theta. And so we get t of x is equal to 0.45 times 16 over 1.8 sine theta. And doing some algebra, we get, what am I? Oh, yeah, sorry. T sine theta, and we know that t is equal to 4.41 over cosine theta. So moving down the line here, just substituting things in, we know that we end up with 4.41 tangent theta equals 4 over sine theta, and we know that tangent theta is equal to sine over cosine. So we end up getting sine squared over cosine theta, which is equal to 1 minus cosine squared theta over cosine theta. That's just, that's just a trig identity. And so we can end up getting a polynomial function, and I just used a factoring calculator there because I don't know how to factor that. And so this value would not exist because it is going to be more than 1. Just a straight up value of cosine theta cannot be more than 1, so it does not exist. So we get cosine theta is equal to 0.644, and we get theta equals 49.91 degrees. And now that we know theta, we can sub that into our equation from earlier as I put, and we get the tension is equal to 6.85 newtons. And then question number 4, we have a 130-pound wrecking ball attached to a 45-foot long steel cable, and it swings vertically as shown here, so starting point down to there. We want to determine the tension in the cable at different points. It starts at the top of the swing. We're assuming velocity equals 0, as I put there. At the bottom, we know that the speed is 13.2 feet per second. So we draw our diagrams and such, and we know that this is at rest, and we also can add in normal acceleration because it's always going into the curve. And at the moment, no tangential acceleration as well, but this makes it very easy to find our tension in the rope, because since we know these are equal to 0, we know that forces must cancel, and in the y direction, n direction, right? Yeah, part of the weight is going the tangential direction, and part of it's going in the normal direction. And so we get, using just geometry, we know that is equal to 20 degrees, and we get the tension of AB. Sorry, that should be AC, right? Yeah, I guess that should be AC. Oops. I had it semi-right. And we have tension of AC going up directly in line with it, and then we have components of the weight in that direction as well, which is W cosine 20, and that is equal to the weight divided by gravity, but that doesn't actually matter, or times the normal acceleration, which is equal to 0, so we can just cross that out. And doing some algebra, we get T, the tension AC is equal to the weight cosine 20, which is equal to 122.2 pounds. And then for the next part, we have our normal acceleration there, tangential acceleration there, velocity going in that direction at 13.2 feet per second. And then, at this point at the bottom, weight's completely going down tension is completely going up. Both are completely in line with normal acceleration. Nothing in line with tangent acceleration, so that is going to be equal to 0, but that actually doesn't matter here because no forces are in that line. So we know that sum of all forces in the normal direction equals the mass times the normal acceleration, so we got TAD minus the weight is equal to the mass, which is equal to the weight over gravity, times normal acceleration, which is velocity squared over the radius. We were given the radius here, it's 45 feet. And then at that point, we just do some algebra. Again, we know the weight as well. We just plug in some numbers, and we get the tension for AD is equal to 145.6 pounds. And question number 5, this one, actually, I had to, going through the answer key at the end, this got me a bit. It's very, very finite number difference, but it does matter, I guess. The first time I went through this problem, I only accounted for the acceleration in the normal direction when the object was still accelerating in the tangential direction, which changes the acceleration a little bit, which then ends up changing the coefficient of static friction as well. So, again, it was very finite difference, but it does change the answer a bit. So we have drew through a few different things here. This is free body with a kinetic diagram. Z's going up. I wasn't sure which direction to put the velocity in because it's always kind of moving differently, but we have the normal force up and the weight going down, and those counteract each other, so important to know later on. And then I have x going in, and then with the normal acceleration, so in, and y that way, so y would be, if that's x, that would be y at that point, or there, and then there. But it's important to note that it is accelerating that way, so there must be some sort of force going that way with it, which ends up being friction force as well. And then there's a friction force pushing it that way as well to keep it from sliding off. And that's what we're trying to figure out. Yeah. Since it's a constant acceleration of 0.24 meters per second on the turntable, we can use a kinematic equation. And since it takes 10 seconds at 0.24 meters per second, the final velocity is 2.4 meters per second. And so the sum of all forces is equal to the mass times the acceleration and the directions. And once you take away the directional components of this here, I guess we know that the force of static friction is equal to the normal force times the coefficient, and we know that is equal to the mass times gravity, because that is, or normal force is equal to the mass times gravity, because that is what we got from our free body diagram right there, times the coefficient of static friction, and that's equal to the ma, which is the mass times the tangent acceleration plus the normal acceleration. And once we take away the directional components of it to add the total together, we have to square them. Like a squared equals b squared plus c squared, but if we're getting a, it's the square root of b squared plus c squared. And so just for the outright total net acceleration, as I put here, the net acceleration is that way, and that is what we are getting at. Because the friction, that means that the friction has a net acceleration in that way, even though it has components there and there. So, yeah, so it's equal to AT squared plus AN squared. And so we're given the tangent acceleration squared right out of the gate, and then we can calculate the normal acceleration when it begins to slip. That's just v squared over the radius, and we're given the radius 2.5 meters. Plug and chug, get gravity times the coefficient of friction is equal to 2.32, and just divide it by gravity, and we get the coefficient of static friction is equal to 0.236, no units. As you can see, I mean, if you square 0.24, you end up with a very, very small number. So it doesn't really add that much to it, but it does add a little bit, especially after you divided it by nearly 10. So, yeah. And then for question number 6, let's see, we have the orbit of the planet Venus. It's nearly circular, so we're just going to call it circular. And yes, things do change a little bit with circular versus non-circular, but just assuming. And we're given a velocity and distance from the sun, from the center of the sun, which is important than just from the surface. And then we also have the radius of the sun. And so while we're just looking for the acceleration on Venus, which we know, since it's going in a circle, that all acceleration, we're not given any tangential acceleration, but we know that accelerating circularly or normally. So we know that the force that the sun is given off, which is gravity, and we know that force is equal to the gravitational constant times the mass of the sun times the mass of Venus over the radius squared. That's equal to the mass of Venus times the acceleration of Venus. And so a few things cancel out. Mass of Venus cancels out. 1r cancels out, and we have the velocity of Venus. We do not have the mass of the sun. We do have the gravitational constant, and we have the radius. So we get the mass of the sun to be 1.999 by 10 to the 30th kilograms. We did have to do a bit of conversions there as well. And then the acceleration of gravity at the surface of the sun. And so, again, we know masses are going to cancel, and we're just since it literally says we're looking for the acceleration of gravity, we're just putting it as g, and this means that we are doing the radius is equal to the radius of the sun itself. Again, we could have saved gm there, but everything we know is just plug and chug. This free body diagram is literally just y is equal to mg. Now that doesn't even actually matter in this case. But we know the force is equal to that gravitational constant times the mass of the sun times the secondary mass over r squared. And we get that the gravity of the sun is equal to 276.1 meters per second squared. Then here, this is kind of just calculus and algebra problem mixed in. So here we have a given, and we're just trying to say that f is inversely proportional to the square of the distance r from the particle to the center of the force O. So, we know that u is equal to 1 over r. So you just take the inverse of r, pretty much. That is given here. And we know that du over, well, we're basically looking to plug things into this part of the equation. It was also given in the notes. So we take the derivative of u with respect to theta, and we get sine of theta over r0, and then take the secondary derivative, and we get cosine theta over r0. And so if we plug these into this left-hand side here, we end up cosine thetas cancel, and we get 2 over r0 is equal to the force over the mass times, angular momentum squared times u squared, which is 1 over r. So rearrange some things there, and then do some algebra, and we get to our final step. And see that f is equal to 2mh, 2 times m times h squared over r0 times r squared. So we know that m, h, and r0 were constants, so pretty much all those are constants, and it's all related to our r right there, which is on the bottom, so it is inversely related. Let's go, we have 2 questions left. Question 8. Let's see, satellite has a circular orbit at this point, right here for part A. That was a horrible circle, but circular orbit for part A, and we're looking for it's going in circular orbit and what velocity it would need at this point to break away from that circular orbit. So we're actually looking for the increase in speed, so that means we have to find that escape velocity and then see how much it needs to go up from. So first thing we need to do is find its current velocity, right? But actually, first thing we end up doing is finding the mass of the Earth using a similar equation as earlier, I believe, right? Yes, so use the radius of the Earth. That's our value right there. We're looking for F equals ma. The only force that we're looking for is gravity. So universal constant, mass of the Earth, mass 2, the radius of the Earth is equal to the mass times the acceleration of gravity. Secondary masses cancel out, and we have the acceleration of gravity on Earth, 9.81, at least in metric, and rearranging, mass of the Earth is 5.97 times 10 to the 24th kilograms. And from the book or notes, we know that the escape velocity is easily determined right there. Is equal to the square root of 2 times g, or universal gravity constant, times m over r0. So we know that the escape velocity from the Earth is at our radius of 25,480,000 meters. You need to be going 5,589.7 meters per second. And for the circular orbit, at this point, we have the force of gravity of the Earth is equal to the mass times the velocity squared over the radius. And so, again, masses cancel. One of the radius is canceled, and we get the velocity squared is equal to the gravitational constant times the mass of the Earth over the radius that it is orbiting. So we get there, plug everything in, we get the velocity of the orbit is 3,952.5 meters per second, and so the delta V must be the change in that, and that shows that the change is 1,637.2 meters per second for part A. And then, right, yeah, then we start part B. that's for the tail. For part B, yes, get this part from the book for elliptical orbits, or this equation, and so you can do some algebra over here. R0 plus R1 over R0 times R1 is equal to 2 times the gravitational constant times the mass of the Earth over angular momentum squared. And so if we can find the angular momentum, we know that angular momentum is equal to the velocity times the radius, and that would allow us to find the velocity to enter the elliptical orbit, or how much it would need to slow down to enter the elliptical orbit. Yeah, so how much it needs to slow down. To enter elliptical orbit. And so again, given value from the book here, it's also important to note that R0 is typically the closest end of it, and then this is R1, which ends up being A. But that actually, I don't think really matters. But if we can figure out H, sorry, I just did this. I'm totally blanking on why. Oh, yes, sorry. We are doing this to figure out how fast it needs to be going and get a velocity to be in the elliptical orbit. And so to get that, we need to find the angular momentum, which is the same at all of these values. Yes, which is the same on all of these values no matter what place. So let's just say a little bit shorter radius here than over here. That means that the velocity is going to be higher up here. That means that the velocity is going to be the highest at the smallest radial point. And so once we plug everything in from rearranging our equation from the book, we get our angular momentum. We can get the velocity at the velocity at A. I guess I can put R of A there, or R1, because that's the point where we're looking to enter it, and after plugging everything in, we get 3,227.2 meters per second. Delta V is equal to velocity while in the circular orbit minus the velocity of the ellipse, and we get that the change in velocity needs to be 725.3 meters per second, which actually, we should flip-flop these, I guess, but how much it needs to slow down to enter that orbit. And then for part C, just the eccentricity of it, and we know that for an ellipse to be happening, the eccentricity must be less than 1. That's given in the book, but we know that we're looking to enter an elliptical orbit, so that's why I assumed that equation was good to use. And we have another given equation, and it's important to note that C is a constant all orbits have a constant C. It's not the same constant though for all. It varies from orbit to orbit, but no matter again what point it's at, the C is the same for that whole orbital path. And so we can use that to our advantage because we have different R's, and these values do not change at all theta does, though, it's important to note that, put it here, but theta equals 0 at the shortest point, and that it equals 180 at the furthest point. So, with that being said, actually need that for the next problem, because we just need to find C at one point, or the correct point, making sure we're using the right value, or at one point using the right values. And once we find C, we can find the eccentricity. And so at the shortest point, theta equals 0, so cosine of the 0 equals 1, and then 1 over r1 equals gravitational constant times the mass of Earth over angular momentum squared plus c. Do some algebra, we find c equals 1.9623 by 10 to the 8th, negative 8th per meter. And then, again, just do more plugging and chugging into the eccentricity, and we get that the eccentricity is equal to 0.333, repeating, which checks out. E less than 1 equals ellipse. And for number 9, we are going to use the same equation, and we know that angular momentum is conserved. Again, h equals r0, v0 times v0 equals the radius times velocity at any point. So here, do a bit of setup, bit of rearranging. R0 and closest point, theta equals 0. That's a big part. And then furthest point, theta equals 180. So we can use these, and we know that since c is constant no matter what, we can get these two equations, or we can make two equations equal each other. And so plug in what we do know, which is not a lot, but that's okay. We're just trying to show, in theory by the end, that that is legit. So once we rearrange these two equations, after plugging in our theta values, we set them equal to each other, do some more algebra, crossing outs, some adding ups. We get 2 times the gravitational constant times the mass of whatever the center is over the angular momentum squared is equal to the 1 over the smallest radius plus 1 over the next, or whatever other radius we want, but of our furthest radius to r1. And what we get is, what we can rearrange to is that g times m over h squared is equal to 1/2 times 1 over r0 plus 1 over r1. And we know that force is equal to the m times normal acceleration, and we know that F is equal to the gravitational force, or universal gravitational law. So we get m times v squared, g times m times little m over r squared is equal to m, or little m, times v squared over the radius. And so little m's cancel. Let's see, you can send the v squared over and cancel it on the right side, so we get r1 over p. In any other case, we could just take that out, but we're looking for 1 over radius instantaneous curvature, and then we can change that to v squared times r squared is equal to h squared, because h equals v times r. And since 1 over the rho, or instantaneous curvature, is equal to g times m, or big M, over h squared, guess what that's equal to? That guy. So we get that 1 over rho is equal to 1/2 times 1 over r0 plus 1 over r1, which is exactly what we get right there.